Hello everyone, welcome to the lecture on orders of convergence. In the previous lectures, we studied the properties of the converging function g of x. Our motivation is still the same. We want to find the solution of the equation f of x equals 0 where f of x is the nonlinear function. And to solve that one, using the fixed point method, we converted the f of x into g of x minus x, where g of x is the converging function. Now, so in the previous lectures, we learned that not all form of g of x are convergent. Okay, there are some g of x divergent. We excluded those. Only convergent function contain the fixed point. So by using the contraction mapping theorem, we can find or choose the convergent function. This theorem, the contraction mapping theorem, tells us that if x naught is in the contraction length, means x naught is the initial point to start the iteration, and L is the contraction mapping length that we defined in the last lecture. Then the mapping g of x is starting with x equal to x naught will converge to a point after enough iterations. That is guaranteed. If x naught is closer to the fixed point, then the iteration number is also same. That means we need less number of iteration to get the fixed point. The next question is how fast is the iteration? What it means is the following. For different choice of x naught, the number of iterations required is different. Okay, so as we choose the point x naught close to the fixed point, so iteration number is less and less. So how fast is the convergence rate? That is the point. The condition lambda is less than 1 just tells us that there is convergence, but it does not tell us how fast the convergence is. In this lecture, we will classify the types of convergence. In the previous lecture, we already learned that for convergence, we must have the following conditions satisfied. Remember that we define the lambda as a derivative of g at the fixed point. Okay? That is x equal to xr. And this must be less than 1 if the function is convergent. Otherwise, it is not. It may be divergent or maybe no contraction at all. Okay. Let us now explore a bit more to find out the rate of convergence. Note from the previous lecture that for a pair of points x and y, both in the contraction length, then we can define the ratio g of y minus g of x divided by y minus x. Remember that the y minus x is the length or distance between the pair of points x and y where iteration starts, and g of y minus g of x is the length or distance between these 2 points after some iterations. So this is the ratio of the length, and since g are converging functions, this ratio in general has to be less than 1, but it will be equal to 1 if the distance remains same, which means that x is the fixed point and y is also the fixed point. If it is the fixed point, by definition the mapping cannot contract any further. It is already the fixed point, so that's why the distance remains same. As a result, ratio becomes 1. So this is true that if and only if both x and y are fixed point of g. So there is a word missing, fixed point of g, and L is of course the contraction length. Now let's choose that x is the fixed point and y is the not fixed point. That means when we apply the iteration, the y has been mapped in a different value and get close to the fixed point. Okay, that's why y equal to x sub k. K is the iteration number. Then as k goes to infinity, then we wrote that lambda equal to limit of k goes to infinity g of x star minus g of xk divided by x star minus xk, absolute value by definition. And you remember that so this equality, actually I wrote it down in the sense of the limit of k goes to infinity. Okay, as k goes to infinity, the point xk approaches x star. So in this sense, I can rewrite or express this limit in this format. Limit xk goes to x star. But remember that here the k goes to infinity is implicitly understood. Without that one, this uh, uh, factor or ratio or limit cannot be equal to that one unless we imply the meaning of k goes to infinity implicitly here. And this ratio in the limiting sense is a constant. Okay, that is a condition for a converging function, and this constant must be less than 1 fraction. Okay. Note that this constant is understood only in the limiting sense, but for any finite value of k, lambda must be less than 1 fraction, but may not be a constant. That means as we increase the iteration number, so value of lambda might be changing, but it must become a constant after sufficient number of iteration, and this constant has to be less than 1. That's what it means here. So before exploring when and how lambda might be a constant or not, let's recall some facts or notions from the computation we did in the previous two lectures. First, some uh, definitions. X star minus xk absolute value, this one is known as the error after kth iteration. That means error means deviation from the actual value or fixed point, and this is also equal to the length or distance between these 2 points x star and xk. That is a geometrical interpretation. Similarly here, gx star minus gxk absolute value, that is also which is same as x star minus xk plus 1, which is the error after k plus 1th iteration, and of course also distance between these 2 points as well. So this two ratio has to be less than 1 for each k and decreases as k increases. It is very obvious that this concept whatever we have in this slide actually is the summary of the short summary of the previous lecture. Now let's consider that g of x equal to root over 2x plus 3. That is one of the converging function that we found in the last lecture. And note that this function has been derived for the original function f of x equal to x square minus 2x minus 3, which has a root minus 1 and 3. And this function g of x can only converge to 3, not minus 1. That has also been explained in the last video lecture. Okay, so let's see what happens here. We do the analysis again. So we copy the result or from the text here to explain here. So xk is the value after a certain iteration, and that is the deviation from the fixed point. Number 3 is the x star here. Okay, so that means this second column is the x star minus xk, and third column is the ratio. Look at here, 3 minus xk is the distance for the k after kth iteration, and 3 minus xk minus 1 is the distance before the kth iteration, that means k minus 1 iteration. Okay, so that means this is the denominator is the previous length and the numerator is the length after the iteration. Okay, So what we do here is the following. We compute the values by using this iteration formula, and you can see here we are choosing actually 11 significant figure for better understanding. So x, you can see here starting from 0 is 1.732. That means actually this second entry is the root over 3, and then it continues, and you can see this is the error uh, in the iteration decreasing, starting from 3, 1.2645, and it is decreasing. Third column, the ratio also decreasing. The important point here is the following: as the xk approaches the fixed value 3, the error approaches 0, and the ratio approaches a fixed number 1/3. Okay, actually it is 0.33333 something. Okay, but since we are considering up to 11 significant figure, so within this figure that is 0, and that is 3, and that is 1/3 approximately. So this is the value of lambda here in the limiting sense, as k goes to very large number. Okay. Notice in the last row here we already considered 11 significant figure that I already explained. This is also known as the error bound, which can be written as this way, or maybe other values like machine epsilon or anything else. So that is the new thing here. The lambda approaches 1/3. How does it approach 1/3, and how does it become fixed? That is in the last column here. Take the other example here. G of x equal to x square plus 3 divided by 2x minus 2. Remember, this one is also a converging function, and this one actually converges to -1 and 3 depending on how we choose x0. If we choose x0 equal to 0, it converts to -1, which is here, and if we start from x equal to 42, then it converts to 3. But let's choose the starting point as 0. So again we fill up the table here. So first column is the value of x as the iteration increases, and second column is the deviation or error compared to the x star. X star is -1 here, and third column is the ratio. So the numerator is the length or distance after kth iteration, and the denominator is the before the kth iteration. Okay, and again same thing we can observe here. As number of iteration increases, the xk value converts to the x star -1, and the ratio, the difference between these 2 points approaches 0, as it should be, because it is a converging function. That means the xk is converging to x star, and this one, the last column, the ratio approaches 0 here. Remember, our condition was lambda has to be less than 1, so 0 is included. Okay, so but of course these results are computed within 11 sig figure as before. That's why we keep 11 significant figure. So first column is the value, approaching value of xk to the x star. Second one is the error bound, and last column is the lambda value. So lambda is 0 within the same error bound as in the previous slide. So these two examples clearly shows that we have three possibility for lambda. Okay, or ratio or converge rate of what is known as lambda. First one, if lambda equal to 0, the convergence is very fast, and that is what we expect, or not expect, we want. Okay, and this is called the superlinear convergence. This is the fastest convergence that we can have here. Second case, we have lambda is less than 1 but greater than 0, is a non-zero finite number. The convergence is certain but not as fast as in the previous case, means superlinear. This one is known as the linear convergence. Third choice, the third possibility is lambda equal to 1. The points here are the fixed point already. So for this case, the numerical approximation method is unnecessary because you already know the fixed point. That's why lambda is constant 1, because it means that the distance between the points are not decreasing because they are the fixed point, and hence is completely ignored here. And the last possibility is lambda is greater than 1. This mapping, the mapping here g of x for this case is divergent, and hence no fixed point can be obtained or fixed point does not exist. So we completely ignore this possibility. No need to consider that one. The first two, number 1 and 2 here, the lambda is 0 and lambda is a fraction. These two possibilities are summarized by the theorem marked as 4.5. What does the theorem says? The theorem says that let g prime be continuous. G prime means first derivative of the function g. Okay? It will be continuous in the neighborhood of a fixed point x star equal to g of x star. That means x is a fixed point. Near this point, we assume that g prime is continuous. And suppose that the iteration xk plus 1 plus g of xk converges to x star as k goes to infinity. Then the following must hold. Okay. First one, if g prime absolute value is not equal to 0, then the convergence will be linear with the rate lambda equal to g prime of x star absolute value. And second possibility, if g prime at x star is 0, then the convergence will be superlinear. This is the fastest convergence. Examples, let's take we recall from the last lecture the sum of gx that we used before. For g of x equal to 2x plus 3 root over, so we compute the lambda here, so take the derivative and put x equal to 3, means x star. So it is pretty simple algebra here, and you compute, and that is equal to 1/3, which is less than 1. And second choice, if we choose g of x equal to x square plus 3 divided by 2x minus 2, then let's compute again g prime at -1. So it is straightforward algebra to do the derivative here, and then that is the derivative. Now put x equal to -1, then it becomes this is equal to 0. So and this is the superlinear case. That's why this one was converged to -1 very fast. I think it is the only third iteration. And also you can consider the interval bisection method. You can see that in that method every interval was reduced to half of the previous interval. That's why clearly lambda has to be half, because that is the interval bisection method if you think in the rate in this sense. Okay, so that is all about the orders of convergence. But for the superlinear case, when lambda equals 0, so it does not mean that higher derivative of g is also 0. Remember that in calculus, that if you have a function in f, if first derivative of f is 0, it does not guarantee that second derivative, third derivative is also 0. Okay, so the question is the following, that for a superlinear case, we want to find a constant value for the convergence as in linear case. Okay, but for the simple ratio or this first derivative, it is equal to 0. The question remains, is the higher derivative is also 0? So based on the fact that higher derivative or higher order ratio may become a constant like a linear convergence case, depending on that one, we can further classify the superlinear case like a order of quadratic convergence or cubic convergence, like that one. So this is not very important. I'm just mentioning for the sake of completeness. But in the next chapter, when we discuss the Newton's method to find the root, then this order of superlinear convergence will come up, and we may say some notion there. Okay, thank you very much for listening to this video. If you have any question, you can come to the live session, or you can post your comment on the discussion board. Okay, thank you very much, and stay safe, be safe. Bye bye.